Group theory in vibrational spectroscopy or IR spectroscopy part 3. In earlier session, we have seen that water molecule can be decomposed into three-dimensional Cartesian coordinates such as 1 shown here or see this, and by doing so, we can construct a set of matrices. So because each atom is decomposed into three-dimensional Cartesian coordinate system, you get a 9 by 9 matrix for various symmetry elements, and C in C2, the diagonal sum is -1. So the character for C2 happens to be -1. And once we obtain the various characters by constructing matrices, then we can decompose them into their irreducible components by making use of what we call as the standard direction formula. In this, we have reached to the conclusion that the total motions, that is translational, rotational, and vibrational, the sum is 3a1 plus a2 plus 2b1 plus 3b2 for water molecule. And we if subtract the translational and rotational degrees of motion from the total reducible by observing the character table to this point group, then we reach to a conclusion that there are fundamental modes of vibrations. They are A1 and B2 type. And again, by looking at the character table, it is possible to predict the IR or Raman activity of such modes of vibrations. So this was all. Now next, I am your instructor Saurabh, and we are going to the next journey of the part 3 spectroscopy. We have seen that the entire procedure that we have described earlier, that is to construct a matrix. In case of water molecule, you had a 9 by 9 matrix. Had it been a benzene molecule, you would have a 36 into 36 order matrix. And clearly, for such all the number of elements and operations, the huge number of matrices will be of no use. And this transformation and manipulation of these matrices will be cumbersome, will be complicated, isn't it? So there must be some alternative methods. Before going in detail of that, just recall the fact. Number one, we observe that the characters of only those atoms becomes important which remains unshifted during the symmetry operations, because others do not come in the diagonal of that particular matrix. The number of unshifted atoms contribute in the character of symmetry operation only because the shifted elements are off diagonal. And recall that every symmetry operation has a matrix representation. So we'll go for the matrix representation of various symmetry operations and then we'll proceed forward. If we look forward for the various matrices such as here, shown here, for identity, for inversion and for rotation, there are 3 matrices have been shown, and the characters are obviously the diagonal sum of the elements. For identity is 3, for inversion it is -3, and for rotation it is cos theta and 1, that is 2 cos theta plus 1. And similarly, if we talk about any plane or sigma xz plane or sigma yz plane, it hardly makes a difference, but in each case the coordinates of that axis gets reflected, which is not contained in the plane, and therefore the contribution of character per unshifted atom comes out to be 1. If we talk about the improper rotation around the z-axis, then we see that in the proper rotation it was 2 cos theta plus 1. And recalling the fact that the axis must be perpendicular to the plane, so if we are using an xy plane, z must be a principal axis and must get reflected. So the coordinates of z are getting reflected, and in that particular case, the coordinates of z are changed to -1, as you can see in this case, and therefore if you go for the diagonal sum cos theta plus cos theta minus 1, that becomes 2 cos theta minus 1. So that is the contribution of character per unshifted atom. Now, if you wish to sum up, for identity, the contribution per unshifted atom is 3. For inversion, it is -3. For rotation along the z-axis is 2 cos theta plus 1. For improper rotation, it is 2 cos theta minus 1. And for reflection, it is 1, irrespective of the type of the plane that we choose. So once we are concerned, once we are decided with it, now we can go for the problem that we have discussed earlier by the construction of matrices. If we notice that we are going to apply the 4 symmetry operations to the water molecule, for identity there are 3 atoms and each contribution comes 3. So for 3 atoms the total contribution is 9. For C2 only 1 oxygen remains unshifted, rest of the hydrogens get moved, and in the expression 2 cos 180 degrees plus 1, because the 180-degree rotation is the C2 axis that results in -1. Remember that cos 180 is -1. Talking about any kind of plane, so if you're talking about the sigma yz plane, only oxygen gets unshifted, its contribution is 1, so atom is 1, so you have one thing. And in xz plane, there are 3 atoms which are unshifted, and the contribution from the plane comes out to be 1, so the contribution total is 3. So this is the same thing, 9 minus 1, 1 and 3, we get the same thing that we have done earlier, and we can further go with this kind of result. Take another example. In the case of ammonia molecule, there are 3 vertical planes and a C3 rotational axis, referring to the number of operations that are there in the character table of the point of C3V. Identity, C3 and sigma V. One identity, 2 C3 and 3 sigma V. So in identity, because in ammonia there are 4 atoms and contribution per atom is 3. So for 4 atoms, it is 4 into 3 is 12. For C3, because the excess passes through only nitrogen atoms, so rest of all the hydrogens are moved, your expression is 2 cos 180 degree plus 1. Cos 180 degree is minus half, so expression is 0. So for a C3 axis, this is going to be always 0 because number of unshifted atoms may be anything, but the contribution of character is 0. And if you're talking about vertical plane, so that each time nitrogen and hydrogen would be there in the plane, reflecting the rest of the hydrogen. So contribution of character per unshifted atom is 1, and there are such 2 atoms. So the total contribution is 1202. Once we have this, then we can further see the character table 1202, and it can be decomposed into their irreducible components by using the standard reduction formula. So what does this formula do is that say if you want to see how many A1s are there in the toe reducible, what we will do is we'll take 12 into 1 into 1 plus 0 into 1 into 2 plus 2 into 1 into 3, that would make is 18 by 6, that is equal to 3. So we'll conclude that in the reducible representation, A1 has come thrice. We talk about A2, just look at this, 12 into 1 into 1 is 12, plus 0 into 1 into 2 is 2, plus 2 into minus 1, 3 is minus 6. The total drops is equal to 0. So total is 6, and 6 by 6 is 1. So A2 comes once in this expression. If we talk about the E representation, 12 into 2 into 1, that is 24. 0 into minus 1 into 2, that becomes 0. And 2 into 0 into 3, that is again 0. So the expression gives 24. 24 divided by 6, that is equal to 4. So the entire expression finally gives out the result that it is equal to 3A1 plus A2 plus 4E. We can further see that this result is correct by saying that A1 and A2 are one-dimensional and E is two-dimensional irreducible representation. So this is 3 plus 1 plus 4 to the 8 plus 1 and 8. So 4 plus 8, that is 12. So there are 3n degrees of freedom in a molecule for 4 atoms. Then there are 4 into 3, that's 12. So this result is correct as far as our theory is concerned. Further, what we are supposed to do is, once we are sure about that then the rest of the things is that we need to subtract rotational and translational motion from it, and then you can get the fundamental modes of vibration. To identify rotational and translational motions from character table, you just refer as whether they have the same symmetry as the Cartesian coordinate or whether they have the same symmetry as that of rotational systems or rotational coordinates. So if we take A2 and E into account for rotational, and if we take A1 into E for translational degree, then we need to subtract it from the entire expression, and after that we'll get some confusion. So toe vibrational is equal to this toe reducible that we have obtained minus 2 rotational and minus 2 translational, that will give you something like this, and this, and this. And finally, the two vibrational degrees will come out to be 2A1 by 2E plus 2E by little computation that you will be able to understand. Because A1 is a one-dimensional and E is two-dimensional, so you have 2 plus 4, that is 6. So total fundamental modes of vibrations are 6, and you will agree with the concept of 3n minus 6 fundamental modes of vibration. So for 12 minus 6 for ammonia molecule, it is again the same. And further, you can see that whether they are coming from IR or non-active vibrations or not. So if they belong to one of the Cartesian coordinate, So A1 is because it is showing Z here. So A1 has to be an IR active vibration, and because there is a binary product here, so it is also Raman active. If we are talking about E, because X and Y are written here, so they are IR active, and because binary product is also written here, so it's also Raman active. So what we conclude is that A1 and E both are the IR and Raman active vibrations. Thanks for watching this video. We'll come with more examples in the next video. Thank you very much again.